thrilled to be able to welcome Professor Nancy Leveson here today. So please, Professor Nancy Leveson, share your presentation. So the presentation will be until 10:20. In fact, it will be until 10:10, and we'll have 10 minutes for questions. And please, everyone, during the presentation, if you have questions, please write in the Slack. And at the end, we'll be able to provide to Professor Nancy Leveson to answer. Thank you. Welcome, Professor.
Thank you. Can you see my screen?
Yes.
Yes, of course.
Okay.
Please show your face also by video.
Okay, good. So thank you. Good morning, everyone. I want to talk about the problem that I see and what a possible solution is. The first problem, the major problem, is that safety and cybersecurity methods that are used today are very expensive and not very effective. Our systems are becoming more complex and more software intensive, and component failures, which is what we used to spend all our time on, are no longer the major problem in safety. Our attempts to prevent cybersecurity problems have not been very successful, given how many penetrations and problems we have. So how do we change safety and security engineering to account for these changes and to solve these problems? Let's start with a general definition of safety. I make a very general definition. An accident equals a mishap equals a loss. That is any undesired and unplanned event that results in a loss. Now that may be human life and injury, which we usually consider, or property damage, but also environmental pollution, mission loss, negative business impact, for example, damage to reputation, product launch delays, legal entanglements, loss of sensitive information. It also includes inadvertent and intentional losses, so security is also treated as a safety problem. System goals, let me explain the difference between, there are certain goals of your system, and there are also constraints or limits on how you can achieve those goals. Safety is usually a constraint on how you achieve your general goal. There are a few systems whose goal is safety, for example, air traffic control, but most of the time safety is a constraint. And finally, safety itself, I define very simply as just absence of losses. The problem that we're dealing with is complexity. Our current tools are all 50 to 75 years old, but our technology is very different today. If you look and see over on the left of this timeline, FMEA was about 1948. Fault trees, HAZOP, event tree analysis, all of these were created in the 1960s. And if you see, there's nothing new except the one Stpa that we created since the 1960s. That's a very long time ago. And all of those old techniques that most people still use assume accidents are caused by component failures. But around the late 1970s, all of a sudden, engineering changed significantly. There was an introduction of computer control, exponential increases in complexity, new technology, changes in the human roles, the role that humans take in systems. And what it meant was, what happened is these old techniques aren't so effective anymore. It's only a random failure, sir. It will never happen again. So what failed here? Some Navy aircraft were carrying missiles from a location to another, and the missiles were on the wing, bottom of the wings of the aircraft where they're usually carried. And one pilot executed a planned test. He was told to do this, and he did, to aim at the aircraft in front and fire a dummy missile just to test the equipment. Nobody involved, however, knew that the software was so-called smart software, and it was designed to substitute a different missile if the one that was commanded to be fired wasn't in a good position. In this case, there was an antenna between the dummy missile and the target, so the software decided to fire a live missile but was located in a better position instead. The live missile was fired at the aircraft in front of the one that was doing the test. So if you think about it, what failed here? Everything worked exactly the way that each component had been designed to work, but together they caused a serious accident. And the problem was in the system design, in the interactions among the components, not in any failure of any of the components. Here's another real accident. It happened in Warsaw when a Lufthansa A320 was landing. The software protects against activating the thrust reversers when the aircraft is in the air, is airborne, because that's dangerous. It will cause the aircraft to stall and crash. Now, when it's landing, it's supposed to allow the thrust reversers to be activated, but there was a lot of water on the runway, and there was hydroplaning and other factors that made the software think that the plane had not landed. So the pilots could not activate the thrust reversers and stop the aircraft, and ran off the end of the runway into a small hill. And you can see the result at the bottom of the slide. Again, nothing failed. Each component worked exactly the way it was designed to work. So there are two types of accidents: component failure accidents, which are usually some kind of random failure and some kind of component failure. But there are also increasingly component interaction accidents. They arise in the interactions among the components. They're related to complexity or coupling in our system design, which leads to design and system engineering errors, but system errors, not component problems. No components may have failed. Now, it's made worse by the introduction of computers and software, but the problem isn't the software, the computer. The problem is really the system design errors. And this stems from the fact that software allows almost unlimited complexity in our designs. So there is a big problem with confusing safety and reliability. In the green circle, we see the scenarios involving failures. In the pink circle are the scenarios leading to accidents. Now, in area A, the system is unreliable, but not unsafe. And FMEA can handle that. In area C, the overlap between the two circles, The system may be unreliable and unsafe, and fault tree analysis, HAZOP, failure modes and effect criticality analysis, Stpa, the new one I'm going to teach you, everything handles this. The problem is area B, where it's unsafe, but not unreliable. Nothing has failed, and only Stpa can handle that. Let's look a little more at software. Software has revolutionized engineering. Now there is software in everything, and it doesn't fail. Software is simply the design of a machine abstracted from its physical realization. We have a general purpose machine or computer. We add software and we get a special purpose machine. So if we add software that's designed of an autopilot, we get an autopilot. If we add software that's designed as accounting system, then it becomes an accounting machine. Software is pure design. Designs do not fail. It also allows almost unlimited system complexity, which means that we can no longer plan, understand, anticipate, and guard against all undesired system behavior, and we cannot exhaustively test to get out all design errors. Now, there's something I think it's important to notice. Context determines whether software is safe. The Ariane 4 software was safe, but when it was reused in the Ariane 5, the exact same software made the spacecraft explode. The software was not safe or unsafe. It all depends on the context in which it's used. So there's a lot of people who talk about safety integrity level, and they assign that to software, but it makes no technical sense. It's technically meaningless because the software itself is not safe or unsafe. So it's not possible to look at software alone and determine its safety and then say it will be safe or unsafe in any system in which you use it. It makes no sense. Let's think about a butter knife. Is that safe or unsafe? Well, it depends upon the context. In the hands of the little boy here, it is definitely unsafe. Finally, the role of software in accidents almost always involves flawed requirements. There are incomplete or wrong assumptions about the operation of the controlled system or the required operation of the computer, and there are unhandled controlled system states and environmental conditions. That's not a problem in the software, that's a problem in the requirements. But look what happens. We spend most of our time with safety integrity level, or sometimes in other standards, they talk about level of rigor in producing the software, or another term used, DAL, design assurance level. But software integrity level of rigor, DAL, has almost nothing to do with system safety because it's in the requirements that's the problem, not in the design of the software. So software assurance shows that the software implements the specified requirements up here, but in the losses related to software, it's usually doing exactly what the software engineers intended it to do, as in those two examples I showed you, although I could tell you dozens and spend hours showing you examples. The lesson we need to learn here is that accidents today don't just result from component failures. We need to consider system design errors, and software contributes differently to accidents than hardware. It doesn't fail, but it can contribute to unsafe behavior, including unsafe human behavior, and we'll talk about that next. It adds almost unlimited complexity, but we can't exhaustively test systems with software in it. And as I said, software itself is not safe or unsafe. So it only can be considered the safety within the specific context in which it's being used. So let's look at humans. Software changes the role of humans in systems. Traditionally, we assume that operator error is the cause of most incidents and accidents, so we should do something about the operator involved or do something about operators in general. Marginalize them by putting in more automation between them and the system they're controlling, or rigidify their work by creating more rules and procedures that they usually cannot follow. Fumbling for his recline button, Ted unwittingly instigates a disaster. All human behavior is impacted, is affected by the context in which it occurs. Here's another accident involving thrust reversers. This was a Tupolev aircraft in Moscow in 2014. And there was a soft touchdown, which made runway contact a little later than usual. There was also a crosswind. And this meant that the weight on wheel switches did not activate. And again, we had that same problem as in Warsaw. The thrust reverse system would not deploy because the software did not think that the plane had landed. The pilots, however, this was a little different because the pilots believed that the thrust reversers would deploy like they always do. So with limited runway space, remember they landed a little late. They quickly engaged high engine power to stop quicker. Instead, because the thrust reversers were not working, were not deployed, the aircraft accelerated forward, eventually colliding with a highway embankment. In complex systems, humans and technical considerations cannot be isolated, although we usually try to do that. We have the human factors, people working separately from the engineers. So the human factors primarily concentrate Now, can you hear me?
Oh, yes, we can. Great.
Great, thank you.
Okay, so the bottom line is that human error is a symptom of a system that needs to be redesigned. So, lesson learned, we cannot effectively reduce accidents without integrating human software and hardware engineering. This other thing I want to say is about an integrated approach to safety and security. We have been incredibly unsuccessful in keeping adversaries out of our systems. They break into our computers hourly. Every minute there's somebody breaking into computers. So it's not working what we're doing. We cannot keep people out. Instead, the alternative is to ensure that if they get in, they cannot do anything harmful. And what that means is we can treat safety and cybersecurity identically. It doesn't really matter whether the operator did something wrong accidentally or because they were tricked or got wrong information and did it the wrong thing on purpose. it's still the same wrong thing. So we may have to add new causes to our analysis, but the rest of the process is exactly the same. So we can use our tools for both safety and cybersecurity, and we are right now. So a summary. This I won't go through this again, but these are the lessons we learned. We need to consider design errors. Software is, the problem is identifying requirements. We have to integrate human software and hardware engineering, and keeping people is out. So we need to change our approach to cybersecurity. We need models and tools that handle hardware and it should be, and hardware failures, software, particularly requirements, human factors, interactions among system components, system design errors, management, regulation, policy, environmental factors, and what engineers call the unknown unknowns, and the interactions among all these things. And that's what the new tools and new approach I'm going to tell you about does. The bottom line, we need something new. We can't just pretend there's no problem or try to shoehorn or, force the new technology and new levels of complexity into those very old models. It doesn't work. The solution requires a paradigm change. Again, the problem is complexity. There are several ways to deal with complexity: analytic decomposition, statistics, and system theory. Let's look at each of these. Analytic decomposition is what everyone does now. Uh-oh, can you hear me still?
Yes.
Oh, okay.
Yes.
I heard somebody. Okay. So the process, we have a process, and what we do is break the process into pieces and analyze or examine the pieces separately and combine the results. And so we look at the reliability of each of the components, we combine that for a system reliability. And it works for some problems. It no longer works for most of the systems we have today. But it's what we typically do. This is what's done in aircraft certification. We divide each of the aircraft functions into a bunch of different functions, controlling the flight path, determine the orientation. We take each of these functions and we can decompose them. And then we go bottom up and combine the probability of failure of each of these functions until we get to a probability of failure of the system as a whole. The problem is that assumes that the interactions of our systems are relatively simple and the components operate independently. That assumption is no longer true in today's tightly coupled, software-intensive, highly automated, connected engineered system. We need a new theoretical basis, and system theory can provide it. System theory was invented in the 1950s, 1960s, because of the complexity of the systems we were building and to try to deal with that complexity. So this is the paradigm change. System theory says we have a process with components, and when the components interact, it creates emergent properties. These emergent properties arise from complex interactions. You've probably heard the phrase, the whole is greater than the sum of its parts. That's really what we mean by emergence. So we need to start in complex systems by looking at the system as a whole. This may sound impossible, but it's actually easier and better than trying to break it into pieces. Safety and security are emergent properties. If I look at just one piece of a system, I look at a valve and I say, this valve is being used in your aircraft or your car. Will the car be safe? And you say, I can't tell you that. You know, I can't answer that question. It depends on how the valve is used. And that's exactly the problem. So if the problem is in the interactions among the components, then what we can do is control these emergent properties or enforce safety constraints on the behavior of the individual components, but also on the component interactions between things. And if you look here, you see most of you will recognize a feedback control loop. The controller issues control actions on these on the system as a whole. The controls of the controllers enforce the safety constraints, like two aircraft or automobiles must not violate minimum separation. Aircraft must maintain sufficient lift. Workers must not be exposed to workplace hazards. The public health system must prevent exposure of the public to contaminated water and food products or to coronaviruses. These are the high-level functional safety security requirements that need to be addressed during design. The paradigm change is to change from prevent failures or treat safety as a reliability problem. Instead, we try to enforce the safety constraints and treat safety as a control problem, not a failure problem. Now, this is a very broad view of control. Component failures and unsafe redundancy, interlocks, and so on, or through process, manufacturing processes and procedures, maintenance, operational processes, or even through social controls, government regulatory authorities, culture, insurance, the law, individual self-interest. All of these are controls that we want to use to maintain the safety constraints. So let's look a little bit more at treating safety as a control problem. We have a controller and we have a control process. The controller always has some kind of algorithm or decision process, and the controller may be a human or it may be a software. It doesn't matter. Both in software or humans and controllers all have a process model. The process model is a model of the state of the control process. The controller makes decisions about what to do, what control actions to provide by using this process model. So the pilot thinks that the reverse thrusters are going to come on. So he issues an acceleration command. Software and human-related accidents often occur when this process model is incorrect. And this model captures software errors, human errors, flawed requirements. It's much better than just say the things fail. So let's look at those two examples that I showed you, the accidents earlier. In Warsaw with the reverse thrusters, the hazard was inadequate aircraft deceleration after landing. So what happened? The aircraft sent feedback indicating the plane did not land. So the software controller says the plane hasn't landed. And so his process model believes that the plane hasn't landed. The pilot can see that the plane has landed. He landed it. So the pilot's process model says the plane has landed. So the pilot issues a command to turn on the reverse thrusters. But the software controller says, I'm going to ignore that command because this plane hasn't landed. All right. So that explains why. Now we can use this to explain why accidents occur after the fact, but we can also use it to identify how to prevent these kinds of accidents from happening before they happen. Way. Remember, the reverse thrust, the plane thought that the software thought that the plane had not landed and therefore ignored the reverse thruster command from the pilot. But this was a little different because the pilot believed that the reverse thrusters would come on. He said, there's a short runway. I need more power to stop. So along with the command to engage the reverse thrusters, he issued a command to engage high engine power. The software command said, well, I'm going to ignore the reverse thruster command, but there's nothing wrong with engaging the high engine power. And that we could do this for the missile release, but I think we don't have time. So it's not just one control loop. What we have is a lot of control loops like this. Over on the right is system operations. On the left is the control structure for system development. And there are little control actions and feedback loops all through this. Over in the right red box is the actual operating process with the human controllers and the physical controller and the automated controllers. Sorry. So the red box on the bottom, let's look more carefully at that. There we have the pilot. We have, which is sending flight commands to the aircraft controller and getting feedback. And also the automatic controller is sending commands to the aircraft and getting feedback. And the pilot may be able to actually get direct commands to the aircraft, physical aircraft. So what this means is that human automation interactions, human hardware interactions, and human-human interactions even. We can look at the interactions, say, between the FAA and the manufacturers and the airlines. So we can use this for social systems. This is a true socio-technical approach. STAMP itself stands for System Theoretic Accident Model and Processes. It's a new, more powerful accident loss causality model. It's based on systems theory. It defines accidents and losses as a dynamic control problem versus a failure problem. It applies to very complex systems. This has been applied to the most complex systems being designed in the world today, and it works. The old techniques, fault trees, familia, you would never be able to apply this to systems that are so complex. But because this is a top-down approach, it works on very complex systems. And it includes all the old scenarios from the traditional hazard analysis methods. It includes those component interaction accidents that I mentioned. It includes software and system design errors. It includes human errors and the entire socio-technical system, not just the technical part. And in fact, we can show that analysis using stamp-based tools produces that the traditional analysis methods produce a subset of the scenarios produced by STAMP. STAMP produces everything, and Sdpa, it produces everything the old techniques produce, everything. This is just a subset, and we can show that mathematically, we can show it empirically. So what kinds of tools are available? Well, STAMP is just the causality model at the bottom. We have tools for accident analysis, something called CAST, a hazard analysis technique called Stpa, security analysis, Stpa-Sec for cybersecurity, organization cultural risk, analysis. We can identify leading indicators of increasing risk. We can use this in model-based system engineering. And if we put the tools together, we can get much more powerful processes, system engineering processes, risk management, regulation, certification, so on. So let's look just very briefly at Stpa. It's a top-down system engineering analysis technique that designs safety and security into systems from the very beginning. Unlike the other techniques, the current techniques where you need a design first, you do not need a design. We will use Stpa to create a safe and secure design from the beginning. It identifies the safety and security constraints or any other emergent property. It identifies the scenarios leading to the violation of the constraints, and then it uses the results. You can use the results, design and redesign the system to be safer. So Stpa is a structured step-by-step analysis method performed on this system model. There's an actual model that you perform this on. Some of it can actually even be automated, some of the analysis. And there's 4 steps, and I'm not going to go through the steps, but I want to show you this is what it generates. At the end, you get design recommendations and component safety and security requirements, such as component A should be able to respond within B seconds to avoid C, or component F shall automatically operate when within G seconds when H. We can also, beyond getting these requirements and design recommendations, we can generate procedures, operator procedures, help with operation training, generate test cases, use them in audits and everything. And every recommendation and decision is traceable back to the hazard it was created to prevent. Next question, of course, is does it work? It is now being used in just about everything, although the most use is now aviation and automobiles and defense. Automobiles, I estimate about 80% of the companies today, auto companies, are using Stpa. And it's not surprising considering how much software and complexity are in automobiles today. We had a workshop this summer at MIT, our 9th year. We had 2,316 registrants from 73 countries, most of them using Stpa. There are standards, especially auto standards, aircraft standards, and defense standards that have been created or are in development. Virtually every standards organization now has Stpa in a standard of some type. Does it work? Well, there have been hundreds of evaluations and comparisons with traditional approaches that are used now. Many of these are controlled scientific comparisons. Some of them are empirical. all that were done correctly. There have been a few other people have done where they didn't do Stpa correctly, but all the rest of them show that Stpa is better. It identifies more critical requirements or design flaws. And it identified real accidents that the other methods missed. One of the reasons we've been looking at the accidents involving the reverse thrusters on aircraft is that we found those using Stpa on an aircraft design, and we went back and said, has this happened? And it turns out it has. And the reason it's happened because the standards and the techniques used today can't find those. Only Stpa does. And everybody that's measured show that this is surprising. Stpa requires orders of magnitude fewer resources than traditional techniques. We don't know about a return on investment. We're only getting some estimates now. One large defense industry contractor that uses Stpa extensively claims that they have saved billions of dollars by using Stpa, mainly because they find the errors early. They don't build the errors in, they get them out from the beginning. The high costs involved, and one of the highest costs in design is going back and changing errors later. And that is eliminated. Here's one small real example of a experiment we were involved in. People were doing an Stpa analysis on a system that had used HAZOP and FMEA on it. So let's assume it's about $150 per hour labor. The Stpa cost for this application was $4,800, but it identified a $1 million design flaw. HAZOP and FMEA were more costly, and they both missed the flaw. Here's the cost. Stpa cost is very low. It's much cheaper than doing these other things, especially FMEA. And these other HAZOP and FMEA did not find the design flaw. Stpa did. Some other uses it's being used on: workplace safety, hospital or healthcare safety, designed for safe manufacturing or assembly at a very large defense firm, production engineering. A John Deere, which makes farm equipment, is using it for a different property. Remember I said it works for any emergent property. This person at John Deere used it to analyze serviceability and diagnostics for this farm equipment. It's been used in organizational analysis. For example, the system engineering process itself, it was used to analyze. It's been used in supply chain analysis. We're now working on improving risk assessment using Stpa. And we're also using it to identify leading indicators of increasing risk. For example, an international airline, we used it on to show how we could take the FOCA data, the data that is that they get from different pieces of the plane. They get something like 5 gigabytes of data a week. This large major airline, when risk was increasing and they were likely to have an accident. So to finish, I can't believe I'm on time. To make progress, we need to develop and use different approaches that match the world of engineering today. These have to consider the entire socio-technical system, not just the operators, not just the hardware and software, but the whole system working together. We need to focus on building safety and security in rather than assuring or measuring it after design is completed. Our systems today are too complex to just assure safety at the end or to measure it. It just doesn't work. Because of the complexity of the systems we're attempting to build, we need to build the security and safety in from the beginning. Abraham Lincoln, our famous president, said that the best way to predict the future is to create it. And we need to develop and use new approaches to certification, regulation, risk management, and risk assessment. We keep using the old techniques. They aren't working, but we use them because that's all people know. We have to be willing to use new techniques and to change the way we do engineering because our systems have changed. For more information, there's a website that has all papers, presentations from conferences, tutorial slides, videos, and so on. There's my book, Engineering a Safer World. My editor, publisher doesn't like when I say this, but you can get a free copy of the book, a PDF, from this URL, from this website. We have an Sdpa Handbook. We put it up in March of 2018. There have been now more than 80,000 downloads since then, and it has been translated into Japanese, Chinese, and Korean versions, so you can get a Japanese version, or if anyone is from Chinese or Korea on this whatever in the listing, you can get the other two. And there's a CAST handbook, which is how to investigate accidents. Can you still hear me?
Yeah.
I'm finished.
Yes, well, thank you very much.